In this video, we're going to talk about those types of radioactive decay and what causes them and how to keep track of the results of those radioactive decays when they occur in certain types of nuclei and using transmutation reactions to monitor their progress and what comes of them. So just kind of to remind us, radioactive decay, this is the disintegration of unstable particles. So you have a nucleus, it is unstable, and it starts to break apart. And as it breaks apart, some of that energy that was there, that was making it unstable in the first place, gets released. And that release of radiation is the most dangerous part of radioactive decay because you get a high energy release and you usually get some charged particles that are generated out of this, and the charged particles can do some damage to your skin and your organs and other things. Now, the mode of radioactive decay, remember our band of stability from the previous video, our mode of radioactive decay depends solely on whether we are dealing with nuclei that are neutron rich or neutron poor. And as far as these types of decay are concerned, beta, positron, electron capture, those are going to be the ones that are dictated by neutron rich and neutron poor. The other type of decay, alpha decay, comes primarily when we have heavy isotopes where their atomic number is greater than 83. That's where we're going to see alpha decays primarily. And that's not a neutron rich or neutron poor problem, it's just a mass problem. Once we get past bismuth, it's kind of impossible for stable nuclei to form. Now we can keep track of the results of these radioactive decays using something called a transmutation reaction. A transmutation reaction is really simple. You have a parent nucleus that is a nucleus that was unstable and undergoes decay, and then you have a daughter nucleus. The daughter nucleus is more stable. It is the result of the radiation. And then you have a radioactive particle, and the radioactive particle can be an alpha particle, a beta particle, a gamma ray, neutrons, any number of things. Now, in a transmutation reaction, we keep track of two different things. We keep track of mass numbers, and we keep track of atomic numbers. And so we can think of this as kind of our law of nuclear conservation, which really isn't a thing, but it's kind of a good way for us to frame what's going on in these transmutation reactions. On both sides of the equation, we have to have an equal number of mass numbers. On both sides of the equation, we have to have an equal number of atomic numbers. And so that's what we're looking for. That's what we're going to track. And as we look at each of these individual types of decay, we will see that in action. So let's take a look at our first. The first type of decay is an alpha decay. Now, alpha decay is where we have an unstable nucleus and it spontaneously emits an alpha particle. An alpha particle has a couple of different forms. We can either see it written as 4, 2, and then the Greek letter alpha, which looks like that sideways fish like that. Or we also can see this written as 4, 2, helium. Because an alpha particle essentially is a helium nucleus where we've taken the electrons off of the helium and it is just the nucleus. That's what an alpha particle is. So it is common to see it written either of these two ways. Now, as is mentioned here in the slide, this tends to be the primary mode for our massive nuclides. And again, we're talking about those with an atomic number greater than 83. And so here's a look at a transmutation reaction for an alpha decay. And we can see, okay, we've got uranium-238. So my mass number for the uranium is 238. My atomic number for the uranium is 92. And then on the flip side of the equation, so let's cut this in half here. On the flip side of the equation, I've got an alpha particle, which has a mass number of 4 and an atomic number of 2. And if I didn't know what the other particle was, I could just use my law of conservation here to say, okay, I had 238 on the left-hand side. I've got 4 on the right-hand side. So 234 is left over. That must be my mass number. And on the flip side, I had 92. And I've got 2 over here plus some sort of unknown, which we'll use Z because that's our common notation for atomic number. And so if we do the algebra, then we get that our atomic number is 90. And so we've got a mass number of 234, atomic number of 90. Atomic number 90 corresponds to TH, thorium. And so thorium is the daughter nuclide here. And so, again, using our appropriate terms, the uranium-238 is the parent nuclide. The thorium-234 is the daughter nuclide. And then the alpha particle is our radioactive particle, which in this case was an alpha particle. So that's alpha decay. Now, a common secondary kind of radioactive decay is something called beta decay. Now, beta decay comes in a couple of different forms. What we get here is this process occurs particularly in neutron-rich environments, where we get a proton that is, well, let me rephrase that. We get a neutron that turns into a proton, and we get a negatively charged beta particle coming off it. And so the way to think about this in terms of subatomic particles is we can almost think of as a neutron as being neutral because it has a positive and a negative subatomic particles inside of it. And so if we lose that negative subatomic particle and that little bit of mass that would come with it, then what we have is a positive subatomic particle. That positive subatomic particle with the mass of a neutron, essentially, we would call a proton. And so in beta decay, what we see there is a proton basically coming from a neutron. And for things that are neutron rich, this helps because it's going to help to swing the ratio more toward the proton side and away from the neutron side, which is going to get us closer to stability. And so the example here, we've got carbon-14 decaying into nitrogen-14 and a beta particle. We can see just from looking at our radioactive transmutation reaction here, we started with 14 mass numbers. The beta particle had 0 mass because it's just a small charged subatomic particle, which means that 14 were left over for the daughter nucleus. We had a atomic number of 6, the -1 here, And so how did we get 7 here? Well, -1 for the beta plus whatever this atomic number is going to equal 6. Do my algebra, and that's how I get the 7. Atomic number 7 corresponds to nitrogen. And so that's how we balance this kind of radioactive decay. And so we can look at alpha and beta and recognize that in alpha and beta decays, uranium with an atomic number of 92 is really far away from bismuth at atomic number 83. So what happens often is what we see is a decay series. That is a radioactive particle, which we're starting way up here with uranium-238. May take a long time to get to something that is actually stable. The stable icon here is actually lead-206, atomic number 82. And so to get from here to here, it's no easy path. It's no simple path. It's going to take a series of decays to get there. And so you see an alpha decay, you see a couple of beta decays, you see a series of alpha decays, you get some more beta decays, and it kind of weaves its way down until we get to this stable nucleus. And once we have that stable nucleus, well, then the decay series stops because there's no longer need for radioactivity. But did want to illustrate this process is pretty long often. Now let's take a look at a couple of other types of decay. So positron. Now positrons are also sometimes referred to as beta emissions. And the difference there is that a positron is a +1 charge instead of a -1 charge. And so what's going on here is we get a proton turning into a neutron. And so what we see here is this is where we have neutron poor nuclides. This is how they get into and do what they need to do. But again, we can see the transmutation reaction here shows I had 11 mass numbers before, 11 at the end, 6 mass number, or excuse me, 6 atomic number for carbon. The beta particle is one of the 6, which means that there are 5 left over. Atomic number 5 is boron, and that's where our stable nucleus comes in. Now, there's one other form of beta, similar beta. It's called electron capture. Very similar in effect to a positron emission. We end up at the same place. The mechanism's what gets flipped around. So what happens here is our unstable carbon nucleus grabs a core electron from itself, and we get a proton turning into a neutron. And so the end result is the same. We get the same daughter nucleus, but the mechanism is slightly different, with the capturing of an electron as opposed to the emission of a positron. And so that's where we're going to stop for this particular example. In our last video, we will look at some of the effects of radiation, and we'll also do a couple of examples of transmutation reactions. Until then, have a good day.